All right, guys, so at this point, we've already been looking at exponential and logarithmic functions for a little while now. The most important section of that was when we looked at properties in the previous two videos. And the reason for that is now we are finally ready to start solving exponential and logarithmic equations. And in doing so, this will be useful not only for looking at graphing a little bit later on, but also for looking at some application style problems where we can actually use exponential and logarithmic equations in some real world context. Okay, so let's start by talking about how to solve exponential equations. So if an equation is in exponential form and the variable x is unknown, then what we're going to try to do is convert to logarithmic form. In other words, we're going to use kind of those inverse properties in order to convert to logarithmic form, and that way we get an answer for our variable. Now, when we're solving equations, we're going to have what's called an exact value as well as what's called a decimal approximation. Notice that whenever we give that decimal approximation, we're going to round to the nearest hundredths place. And a lot of times our answers are going to be decimals when we want to see what the number looks like. When we give the exact value, it's really not going to give the answer much details. It's going to be hard to kind of understand what the actual number is, but we're going to go ahead and give both. So let's start with number one. And number one is kind of a special case. This is actually something we would have seen before back in the previous section where we were looking at properties, because this is just the one-to-one property. You've got the base, which is the same on both sides of your equation. That means that your exponents have to be equal to each other as well. So to solve, we can just set 2y equal to 14 and then divide both sides by 2 to get that y is equal to 2. So in this case, because that ends up being a whole number, that's both the exact value and it's really not an approximate value, but really we're just going to have that one single answer. And that doesn't happen very often, but it is possible. Okay, so let's look at number two. So number two, we've got 10 to the power of x is equal to 12. And so to solve, first we would want to try to get the base and the exponent by themselves first, which they already are. 10 to the power of x is by itself on the left side. So now we just need to convert to logarithmic form. So what that means is that we're going to take a log with the same base as the base of our exponent. So that means taking a log base 10 of both sides. And remember, log base 10 is just the common log. So we can just write that as log without a base of both sides. So that would be log of 10x is equal to log of 12. Now, since the log has a base of 10, that allows you to cancel out the log of 10. That leaves you with just x by itself on the left is equal to log of 12 on the right. Now again, at this point, we actually have one of our answers. This is what we would call the exact answer, is that log of 12 would be the solution to this equation. But it really doesn't tell you what the number is approximately. Like if we wanted to know what number, when we take 10 to the power of that number, is about 12, we're going to actually have to use a calculator to find that. So let's go ahead and let's put that into our calculator. So we'll type log of 12 into whatever calculator you are wanting to use. I'm just going to use the Desmos scientific calculator today to show you that. And we get 1.079. So the nearest 100th place, that would be about 1.08. So notice when you write the exact answer, you leave it as equals. When you write the approximate answer, then you just use that approximation symbol, which is the equal sign, but kind of squiggled. And that tells the person looking at the answer that that's just the approximation. In other words, if we were to take 10 to the power of 1.08, and again, we've rounded, so it's not going to be exactly 12, but it's going to give you a number pretty close to 12. So again, that's why we call it the approximation. All right, so let's take a look at number three. So number three, we've got 4 multiplied by 3 to the power of x is equal to 112. So before we can do anything else, we need to get rid of the 4 that's in front of 3x, so we need to divide both sides by 4. So that will give us 3 to the power of x is equal to 112 divided by 4, which, let's see what that is, 28. Okay. So we're asking ourselves 3 to what power is 28? It's going to be a little bit more than 3 because if you think about it, 3 to the third power is 27. So our answer for x should be a little bit more than 3. But before we get there, what we now need to do is we need to take a log on both sides which has the same base as the base of our exponent. So that means taking log base 3 of both sides of our equation. So then on the left-hand side, our log base 3 of 3 is going to cancel, and we're going to get that x is equal to log base 3 of 28. So at that point, we have our exact answer. That would be, if you put it back into the original equation, exactly what you would use to get to your answer. But we want to probably get a decimal approximation for that. So let's go ahead and type that into our calculator. Remember that you're going to have to use change of base formula. So you're going to have to take log of 28 divided by the log of 3 in order to get that decimal approximation. And then when we do that, we end up with, like I said, something that's a little bit more than 3. So 3.03. And there is our decimal approximation. All right. Let's do just a few more examples with exponential functions, and then we can switch over to logarithmic. So number 4, we've got 6 to the power of 2x minus 5 plus 4 is equal to 12. So first thing we need to do is we need to solve for the base of our exponent, which is basically to solve for this 6 to the power of 2x minus 5. So let's start by subtracting 4 from both sides. That's going to give us 6 to the power of 2x minus 5 is equal to 8. And now we need to take a logarithm on both sides, which is the same base as the base of our exponent. So that would be log base 6 of both sides of our equation. So what that's going to leave us with on the left side is 2x minus 5. On the right side, we're going to leave it as log base 6 of 8. You only type that into a calculator when you're done solving for the variable. And there's a little bit more work left to go. If we add 5 to both sides of our equation, then now we're going to have that 2x is equal to log base 6 of 8 plus 5 after it. And then one last step to go, which is that we're going to divide by 2 on both sides of the equation. That will finally give us x by itself, and it's equal to this right here. So this is our exact answer, is log base 6 of 8 plus 5 all over 2. And here's where, again, that exact answer is not going to give you a whole lot of information about what the variable is approximately. So let's go ahead and type that into our calculator, starting with doing change of base formula for log base 6 of 8. So that would be log of 8 divided by log of 6, which is approximately 1.6. Then we're going to take our answer and add 5 to it, which is 6.16. And then we'll take that answer and divide by 2. Or you could probably find a way to type all this in all at once. I was just doing it separately. And that should give you your decimal approximation, which is that x is approximately 3.08. All right, so let's look at just a couple more examples here, and that'll be it for exponential functions. So we've got 3 multiplied by, in parentheses, 4 to the power of 2t plus 7 minus 3 is equal to 12. So let's start by adding the 3 to both sides. That will give us 3 multiplied by your 4 to the power of 2t plus 7 is equal to 15. Now let's go ahead and divide both sides by 3. So that gives you the 4 to the power of 2t plus 7 by itself is equal to 15 divided by 3, which is 5. Now we're ready to go ahead and take a log on both sides. Remember that logarithm needs to be the same base as that base of your exponent to be able to cancel out that base. So that is log base 4 of both sides of your equation. So on the left side, that leaves you with the 2t plus 7. On the right side, we have log base 4 of 5. At which point we now need to continue to solve for t, so we'll subtract 7 from both sides. That'll leave us with 2t being equal to log base 4 of 5 minus 7. And then we divide both sides by 2. That gives us t by itself is equal to, and here's your exact answer, which is log base 4 of 5 minus 7 all over 2. So now to get our approximation, we'll start by using change of base to take log of 5 divided by log of 4. And then we'll take that answer and we will subtract 7 from it. And then take that number and divide it by 2. And that should give us as a decimal negative 2.92. And it is okay to have negative numbers as your answer. Remember, we just cannot take the logarithm of negative numbers. In fact, we'll talk a little bit more about that when we get to logarithms, because there is a chance that you might end up with an extraneous solution. All right, let's take a look at 2 more examples of exponential equations, and then we'll take a look at those logarithmic equations. So number 6, we've got 8e to the power of 2x minus 5 is equal to 56. So let's go ahead and divide both sides by 8. That will give us e to the power of 2x minus 5 is equal to 7. So now we're ready to go ahead and take a log on both sides. Since it's e, we need to take a log base e of both sides, which remember that log base e is just the natural log. So what we're going to do is we're just going to take the natural log of both sides of our equation. When we do that, natural log and e are going to cancel. That leaves us with 2x minus 5 is equal to natural log of 7. So now we just need to solve for x, so add 5 to both sides. And we'll have that 2x is equal to the natural log of 7 plus 5. And then divide both sides by 2. That should give us x by itself is equal to, and then here is the exact answer, which is natural log of 7 plus 5 all over 2. Now, since we don't have to use change of base on this, we just have to type in natural log. You should be able to type this all in at once if you're careful without too much trouble. So that would be natural log of 7 plus 5 all over 2. And that's going to be about 3.47 to the nearest hundredths place. All right, let's take a look at one last example, and that should be it for us. All right, so once again, we need to get our base by itself first. We need to get e by itself. So let's start by dividing both sides by 5. That way, on the left side, we just have 1 plus e to the power of x over 3 is equal to, if we take 8.2 divided by 5, that is 1.64. So now we'll go ahead and subtract 1 from both sides. So that'll be e to the power of x over 3 is equal to 0.64. And now, since we've got the base by itself, we're ready to take natural log of both sides of our equation. And when we do that, on the left side, natural log and e will cancel. That'll leave us with x over 3 is equal to the natural log of 0.64. And now to get x by itself, just take both sides and multiply by 3. That should leave us with x by itself on the left is equal to 3 multiplied by the natural log of 64 on the right. Or natural log of 0.64 rather. All right, so to type this in, this one shouldn't be too bad. We'll take 3 multiplied by the natural log of 0.64, which is approximately negative 1.34 to the nearest hundredths place. And so there's our decimal approximation. Okay, so that pretty much wraps up exponential equations. Let's now talk about logarithmic equations and see how they are slightly similar. In fact, why don't we do this? Just to kind of make a nice transition, nice break, let's go ahead and just do that in a separate video. I will have that for you here shortly.